very classical, right? Maybe to contribute to the Gaussian for the least square. Now, total least square. This problem for mathematically from the 1980. I will show you. This is outline of my talk, actually due to Jim Golub. Jim Golub just passed away maybe six years ago. He is we can say he is the father of matrix computation, or more general computational mathematics of the states. And he is very few elected to the 3 national academics in the US. National of Science, Engineering, and Arts and Science. So this is and his recent book, this one, Matrix Computation. This is the Bible of the matrix computation. It just published the 4th edition last year. This is very. This is one chapter of totally square. In 1980, he used the single value decomposition to solve this totally squares problem. One is for the matrix A and A, another for the AB. Just use the SVD. So this gave the in this condition, he gave the unique solution, existence and unique solution of this solution. The background for this square from totally square from statistics. Before 1980, the statisticians they gave a lot of examples, found is better than the least square. So from the mathematical point of view, Jim Golub and Charles Van Loon, they write the paper, begin this area. And one Korean mathematician, Heisenberg, now in Georgia, Heisenberg is very famous woman mathematician. He used a lot of totally square in application in major things. He used totally square. So the solution you can see is not complicated, it's easy. If you use the SVD, just use singular value, singular vector. This is clear. So our interest is how to get is faster algorithm or the perturbation bound. If we have some perturbation, if data A and data B and the data is not incorrect, have some error. First we have this lemma. This lemma is simple and nice. Also another for the single value, smallest single value. This is due to Peter Stewart. Peter Stewart is also a member of National Academy of Engineering. He gave this lemma. This lemma is simple but very important. For the 2 smallest single value, have this expression: U and V are single vector, left and right single vector. Now we can have this our theory for the perturbation. If the perturbation of is small, then we have this bound. We can say a bound for the totally square, the relative error, with the 2 norm. And this condition, it can be satisfied. If satisfied, this it can be easily checked. It's okay, not too complicated. And another name we will introduce called effective condition number. Effective condition number is this way. Of course, this A is singular, so we use the Morpern's inverse. This is a classical condition number. In the textbook, it is more often introduced this one called condition number, right? This is called effective. From mathematics, you can prove if sometimes much smaller than this one. So in our bound, we introduce this one. This is called the effective condition number. Can be smaller. In some extreme case, it can be much smaller than the classical one. This is our bound in 2009. We gave this formula for the condition number for the totally squares with the canonical product. After that, there are 2 groups. One is this is a French group. They give another bound with this one, with the SVD. They claim they are good. Another group is in China, this Tsinghua University. They also give this bound, also relative condition number with this one. with the Cholistic decomposition, they can find it, this bond. With the Cholistic decomposition, they can find it. Now we prove they're mathematically equivalent. They just give different expression. It's more suitable for computation. So these two bonds. We just show you this for mathematics. It's the same one. Okay, and next part I will introduce a statistical condition number estimation. Alan Lab. Alan is he gave this idea in 1994 and just something time ran it. In that time, his paper published, but didn't make more notice. But for now, it's good. He gave the statistic condition number. Nowadays, statistical condition number is good, as we have some small samples to estimate condition number. Also, he made more contribution in the Descartes equation. He gave some Newton method or something after the Descartes equation. This is so he's an IEEE fellow. And the idea is not difficult. This is just for the Taylor expansion. This first order. So in the usual way, we just found this one. As the first order, just the condition number. If you minus it and divide it delta, so I found the expected value of V, just this one. Expansion. So this is one fact I found. But important is this bond. Usually condition number we will estimate, but it's not easy to estimate. They gave this probability formula between if a llama, of course a llama greater than 1, such as 10 and 1/10, and he gave the probability, and this is lower bound of this one. So it's usually difficult to estimate this one, but he connected with this fact. This fact is familiar with the statistics people. This is a fact. They call it the worst fact, and we can establish it by the expansion of this one. So one is condition number. So if you have example, just two examples, this one, this low bound, just one. This is very close to 1. So the probability is close to 1, then this algorithm is very good. Very good. He have the probability estimation. Usually we just have the numerical algorithm. We cannot guarantee its probability. Just give the high accuracy, but you cannot say the high probability. So this algorithm, he can give this probability. So it's good. We just introduce a vector. It's easy, extended to the matrix valued function. This is easy. Now we can use this method for our total least squares problem. We want to estimate this condition number by this statistical estimation. I will show you the example later. So this is not different. Recently, this 3 is French. This Ireland from States. They gave the LAPAC working note. Gave this one with the least square for the least squares problem. They gave this fast estimation. Now we can use it. For this method for the total least squares. We can use subspace condition number estimation, such as the QR decomposition with our algorithms, and we can get it. This is for component-wise. The original one is for the norm-wise. And we can also do it for the component-wise for this condition number. We can find it. Also, the two French professors gave the Frisch derivatives. The extension just this air. Usually the air is identity matrix. Just cover our case. They extended our result a little bit with this general air we can derive. And this is for the condition number with the abstract for condition number. And this is for the component-wise condition number, we can get algorithms or SC algorithm for it. And the last part I went to the random algorithm. Random algorithm now is popular. I think we should contribute this one. For Yimin locally. For his name, you can see he's from Russia. He's a Russian. And then he moved to the States. Now he's a professor of Yale University in computer science. He is also both national academic engineering and science, economic science. And his fast algorithm for fast multiple, this is very famous. Someone regarded it as one of the top algorithms in 19th centuries. This is a fast and used for algorithm multiple. He published several papers in 2005 or 6 to give the random algorithm for matrix decompositions. So can be get more quickly, efficiently, for such as the classical algorithm can be more quickly. So we just introduced. Another one is a survey in some review, published in 2011. Now we've searched from a Google Scholar, cited by 400 times. He gave the findings judged with a random probability algorithm for approximation for the matrix decompositions. This is a survey, and this is another paper. We know the AA package, LAPACK package. This is developed by Jing Demo, UC Berkeley. They were large groups, so they used this random algorithm, subcharging LAPACK's least squares. They give examples. They found it's quick, efficient than the LAPACK's ALSQ algorithm. This algorithm, and this is my brother study at Wuhan University. Zhoujun is a Chinese University of Hong Kong. They use the random SVD for the ear-pulse problem. They use it for ear-pulse problem. So this is a recent application of random algorithm. So we now use it for our total least squares. First is give a matrix, Gaussian random matrix. This Gaussian random. Then we solve this matrix X with the QR algorithm with the Q. Then we get this Y. Then we use the SVD for the smaller case for the matrix Z. Z is Q and Y. So our algorithm quickly just do this one. You use the SVD for the smaller matrix. Classical method just use the SVD for the large matrix. So this is quickly, and this is accuracy, not just quickly and discrete. The solution just this one. So this is just we call the random algorithm for the total least squares, and just several steps for this algorithm. Also, there's a truncated total least square. As for the ear-pulse problem, the singular values, the smaller singular value are close to 0, then we just truncated it. If it's smaller, such as epsilon, truncated. So we can also have the random algorithm for the truncated SVD. We can also give this similar algorithm for the truncated total least square. This is minimum norm solution, just this one. I will show you the example. How about so the question is, how about the classical numeric algorithm for this problem, such as Langson's process, called partial SVD, but there's a Bros2 operation, which means matrix vector multiplications, just matrix vector. But in our random algorithm, it's just a matrix. So this is called Bros3 operation. So it's more quickly. This is for the ear conditioned totally square. We can also have this algorithm. the advantage is just +3. And also for the discrete yield process problem, they have the GCV or such as error curve, and error curve. This is for the yield process problem. They like this regularization method. So the Lotto method. This is a computational complexity for the random totally squared, the truncated totally squared. So this is for the long source bidiagonal method. This one, the operation complexity. This one, but for the random complexity, this one, almost 1/3. So the complex, you can compare this clearly, and this is for truncated. This one. So our algorithm is efficient in +3 operations. And last part we will show some examples. This is an example from their paper. This one from their paper. We will just show. This is an exact error. If compute this our early bound in 2009, and this is French group. This is the Tsinghua group. Now this is our new bound. So our new bound little bit better. This is our perturbation bound. I will just show you an example. Another one is a classical example for totally square. This is this example. Then we will show that this is also this exact error. This is original bound. This two one. Now you can see this 3 one is mathematical equivalent, is the same, but now a new one is a little bit sharp for the perturbation bound. Another we use our SCE for the random tests. We just show you this rate is just our estimation of the exact condition number. If it's 1, just the perfect, then you can see from SCE just almost a 2. Almost a 2, then the exact one. So this is SCE method. Another is for the accuracy. So you can see. So SCE for such problem is fast and efficient. And the last part I will just show is for the yield process problem. This Hansen, I just see the introduction of your department. He is from the Technical University of Denmark. So now he's very famous for his regularization too. If we did a numerical example, usually use his toolbox. This Hansen from Denmark. So now this is, I just show you. This is our. This is classical totally square. This is a random total square. You can see random algorithm is much fast, but the error. This is two solution is close. Solution is close, but the time is quickly for this problem. And this is well conditioned, and we also tested the yield conditioned case. This is called sure. Example I will show you. Also, this is a time. This is for the random totally square. Now we can show some. This is the sure. For 3, one is exact. This one is the exact solution, and this is least square with the truncated SVD. This traditional truncated SVD, and this our random algorithm. This is one example, and the second we use the for. This is the time. This is random time. This error. 1, 2, 3, 4. These 7 examples. We test the regularization toolbox. I will show you the figure so you can see it clearly. So you can see random algorithm did this figure almost with the classical one. With the classical totally square, almost same, but our time is much smaller, more quickly. And you can see this is another for this test example. This is yield conditioned, and this one is fine. This for this test problem, our algorithm is fine with the exact one, almost the same from this figure. And this is also good. Gravity is good. And this is not so good. This is a heat problem. Our solution, this one. This is not good. This is air conditioned. And this air Laplace. Also, this very air conditioned problem. And this Phillips, this is also testing one. So this is okay. This is okay. And this Shaw for it is okay, I think. So in this talk, we first give a new particular bound for the relative error of total least squares. It seems for your work example, it seems a little bit better than the existing lectures. Another, we use the SC, the statistical condition number estimations for the total least squares. The last part for the random algorithm for the total least square. I think this part is important. It may be used for the regularity parameter. This may be give a new method for the choose the parameter regularity with the random algorithms to translate such a technical regularization. I think maybe, but there's a lot of things can be done with this one, with the parameter choosing for the regularizing problem with the random algorithms. So that's all for my talk. Thank you.